Okay, so now we're going to be discussing about operational amplifiers. So first, operational amplifiers are a three-terminal electronic component that does two things: math and amplifying. There's a few other characteristics that it can do. It can do filters, it can do inverting a signal, so on and so forth. But generally, the name operational amplifiers refers to the fact that it can do math operations and amplifying signals. So first, to discuss about the operational amplifier a lot more, the operational amplifier is generally made up of transistors, made specifically BJTs, MOSFETs, or JFETs. Although more sophisticated models combine with bipolar MOSFETs, could be CMOS, so on and so forth. Usually, generally though, these are more expensive. So we usually use the more commercial ones like BJT, MOSFETs, or JFETs to make operational amplifiers. Some of the famous integrated circuit chips are the LM358, the LM324, and the LM741. And these are three chips that contain an operational amplifier embedded in them to give you what you need for experimental purposes. So with that out of the way, let us show you what an operational amplifier looks like. So first, an operational amplifier has three terminals. It has the non-inverting terminal, the inverting terminal, a value of A, which we denote as an open loop gain, the output voltage, and that's it. Now, this is talking about an unbiased model. That is to say that this model represents an operational amplifier without any power. Without power. Because operational amplifiers are electronic devices, they need power. So in the event that we ask about experimentally how an operational amplifier behaves under experiment, we have to first address a few things. We have to first address what's the gain A, but we also have to address the biasing terminals. So we add two more terminals to them, and usually we denote this as VCC, and maybe this is VEE. These denote 5 volts and negative 5 volts respectively, although they're not always that case. They could be a lot higher and they could be a lot lower. But the terminals remain the same. Now, let us first discuss about the ideal model of an operational amplifier. The characteristics of an ideal operational amplifier is infinite input impedance, or for now we call this resistance, just to keep it simple. Zero output resistance, and infinite gain. The equation to model the two characteristics of an operational amplifier involve the fact that because the input resistance is really high, the input current is equal to each other being zero. In the event that we have also high infinite input resistance, it's almost like we have an open circuit. And what actually ends up happening is that the non-inverting and the inverting terminals are equal to each other, which actually means that if you ground one, you actually ground the other. This is a characteristic called virtual ground. So it's pretty great for electrical isolation as well. Now, in the case of the non-ideal model, we might not have infinite or zero output resistance, but we either have high or low respectively. And infinite gain might not be ideal, but the gain that you might get is really high. So first, let me say that the input current is generally still true. However, for the case of this, the output is different. We have to use this equation instead. This, as mentioned before, is called your open loop gain. This is what you amplify in order to get to your output voltage based on this equation. Now, with this though, this leads to experimental problems, but that's going to be discussed outside of this review. So first, notice that there's not a lot of difference. An open loop gain for this is usually 10 to the 5, maybe 10 to the 6, depending on how sophisticated the models are. If it's maybe created with Darlington arrays that amplify a lot, it might probably reach the upper end of 10 to the 5. And then for more sophisticated models, such as MOSFETs, it might reach 10 to the 6. Now, that's basically the background of operational amplifiers. But what about doing an analysis with them? Well, first, always use nodal analysis. So first, let's do a problem, a very simple one to kind of demonstrate the power of operational amplifiers. So in this case, I'm going to actually switch the terminals. It's going to be negative, positive. An operational amplifier is most useful when we control it through feedback. But we want only one kind of feedback called negative feedback. The idea is that with negative feedback, it serves based on the ideal characteristic. We want the positive and negative terminals to kind of balance each other out all the time. So it leads us to having that negative feedback is better than positive feedback, because positive feedback means we're actually going to keep building it on and on until the output basically is equal to the inputs, which we don't want. We want the inputs equal to each other. Okay, so we have something like this. Let's call this VI. Let's call this R1, R2, and V out. Now, when we're using nodal analysis, focus on everything to the left of the operational amplifier, to left of op amp. Second, find essential nodes. And then solve. So let us find something from this. So first, here's the essential node. Let's call this VA. Okay, so this is VA. Now, using what we know about nodal analysis, let's assign some currents, any direction realistically. So we have Vi minus Va divided R over R1 plus Vo minus Va divided by R2 equal to 0. Now in this case, Va is equal to V minus, which is equal to V plus, which is equal to 0. So this gets canceled out. From here, we actually can get the transfer curve as negative R2 over R1. And this is actually what's called an inverting amplifier.